Again, welcome back to calculus. These lectures cover the product and quotient rules for derivative. So we start with two examples here. We have y equal to 4x squared plus 3 times 2x plus 5. So here we need to use the product rule. So the product rule here will be 4x squared plus 3 times the derivative of 2x plus 5 plus 2x plus 5 times the derivative of 4x squared plus 3. So the derivative of 2x plus 5 will give us 2 times 4x squared plus 3. Then the derivative of 4x squared plus 3 will give us 8x times 2x plus 3. So we multiply 2 by 4x squared plus 3 and we get 8x squared plus 6. We multiply 8x by 2x plus 5 and we get 16x plus 40x. 16x squared plus 40x. So here we can combine the 8x squared plus 16x squared, which will give us 24x squared. Then plus 40x and plus 6. So that will be our final solution. Now the next example, we have a f at x equal to 3x squared minus 5x times ex. Again, here we have two functions multiply. So we need to use the product rule again. So here we can find 3x squared minus 5x times the derivative of ex plus derivative of 3x squared minus 5x times ex. So the derivative of es will give us es, and es times 3x squared minus 5x. Now derivative of 3x squared plus minus 5x will give us 6x minus 5 times the es. Now here we can see es is common in the two terms. So we can bring the es out and combine the two terms. So we get 3x squared minus 5x plus 6x minus 5. 3x squared is by itself. Minus 5x plus 6x will give us plus x and minus 5. So that will be our final solution. Now let's go through the rules. Here we say by analog, with the difference and also the sum rules, we might be tempted to guess, as Leibniz did 3 centuries ago, that the derivative of a product is the product of the derivatives, which is wrong. As we saw the examples here, we cannot say the derivative of 4x squared plus 3 times 2x plus 5 is the derivative of 4x squared plus 3 and 2x, more or less like the sum and also the product rule. The reason why we can see here, if we say f at s equal to x and g at s equal to s squared, then the power rule gives derivative of f at x to be 1 and also g at s to be 2x. Now, if I have f times g x, it means s times s will give me s cubed. And the derivative of s cubed will give me 3s squared. So here we can see that the derivative of fg is not the same as derivative of f and derivative of g, because we get 2x and the other gives us 3s squared. So because of this, we can use the concept of sum and difference rules. If we do that with the sum and difference, it will be the same. So here, if s changes by an amount dx, then the corresponding changes in u and v are the following. So du will give us f at s plus ds minus f at x. And also dv will give us g s at ds minus g at x. So in conclusion, we can say that duv will give us u plus du times v plus dv minus uv, which will give us u dv plus v du plus du dv. And we can see here we have the sum of the 3 shaded areas together. So if we divide by dx, we get the following. So we get duv over dx equal to u dv dx plus v du dx plus du dv dx. Now, we let dx approaches 0 and we take the limit and we get this. And finally, we are going to get u dv dx plus v du dx plus 0 dv dx. So here we can see that in conclusion, we can say that the derivative of uv is equal to u dv dx plus v du dx, which is our previous example we did. So if uv are two functions, to find the derivative of it, it will not be derivative of u times derivative of v, but rather it will be u times the derivative of v plus v times the derivative of u. So that would be the product rule. So if I have a derivative of f at x times g at x, it will give me f at x times the derivative of gx plus gs times the derivative of f at s. It doesn't matter, it can be the opposite. We can find the derivative of f at x first times g at x plus derivative of, again, g at s times s. So it doesn't matter which one we do first. So there's another example here. Let's find the derivative of x times ex. So this will give a derivative of e times x times e to the power x. So this is the same as saying the derivative of ex times x plus the derivative of, again, x times ex. So it doesn't matter. Here we say, okay, x times the derivative of ex plus e to the power s derivative of x. So we know x is down. The rate of es is ex plus ex. The rate of x is 1. So our answer will be s plus 1 times ex, because es is common in the two terms. Now we can find the second derivative. Let's say we have s plus 1 times ex. This means our one function will be s plus 1. The other function is es. So we can say the x plus 1 times the derivative of ex plus ex times the derivative of x plus 1. So again, the derivative of es is ex, and the derivative of s plus 1 is 1 times ex. So our answer will be s plus 2 ex. Now, we can move on to the third derivative. As another example, s plus 3 e to the power x. And the fourth derivative will be, again, s plus 4 times e to the power x. So in fact, we can see the pattern here, which tells us that f to the power n derivative x will give us s plus n times ex. We will see more example of this in the future lectures. So next is the quotient rule. Now with the quotient rule, let's start with example here. I have 6e u to the power 4 minus 5u over u plus 1. Now the rule said that first we can find the derivative of the, here we have to be careful. As we said in the product, it doesn't matter which function we find the derivative first because we add together. But here we always have to find the derivative of the numerator first, then multiply by the denominator minus derivative of the denominator multiplied by the numerator, now divided by the denominator square. Why we have to be careful here? Because of the minus. For example, 2 plus 3 is 5. 2 plus 3 is 5. 3 plus 2 is still 5. But 3 minus 2 is negative 1. And 3 minus 2 is positive 1. So with the difference, there will be a difference in the answer. So that's the rule. Now the only thing left now, we have to simplify the expression. So again, the derivative of the numerator first times the denominator minus the derivative of the denominator times the numerator all over the denominator square. So here we open the bracket and we got 24u to the power 4 minus 5u plus 24u to the power 3 minus 5 minus 6 u to the power 4 plus 5u all over u plus 1 all square. We combine the like term, we can say minus 6u to the power 4, 24u to the power 4. So that will give us 18u to the power 4. We have minus u plus u, so they will cancel. Then we have 24u cubed by itself and minus 5 by itself. So we bring it. So that will be our final solution here. Now let's see the second example. It's a quotient again because we have x, e to the power x, divided by 1 minus e to the power x. So we have two functions divided. So this means we have to find the derivative of the numerator ex first times the denominator minus derivative of the denominator times the numerator. So the derivative of ex will give us ex times 1 minus ex minus, now we find the derivative of 1 minus ex, which will give us minus ex, then minus ex here. All over 1 minus e to the power x or square. Excuse me, to say ex, I mean to say e to the power x. Negative. So here we just do our expression multiply return. We get e to the power x minus e to the power 2x plus e to the power 2x. All over 1 minus e to the power x or square. So here we can see that e to the negative e to the power 2s, we have negative and positive, they cancel. So the final answer will be e to the power x divided by 1 minus e to the power x all square. Now let's go through the rules now. So as we said, if we have du by v, so this is a quotient. It's the same as what we wrote down here, u plus du over v plus dv minus e over v, which will give us u plus du, v minus v, then minus u, v plus dv over, here we find the LCM to combine the two terms. So at the end, we get the expression here. Now, we can also use taking the limit, and this is what we get. And this will prove the formula here for us. So in general, this will be the formula for quotient rule. The derivative of f at x divided by g at x will be the derivative of f at x times g at x minus derivative of g at x times v at x, all divided by g at x all square. And we have another example here, y equal to s squared plus s minus 2 divided by s cubed plus 6. So here we find the derivative of the numerator first, which will give us s squared plus x minus 2 times s cubed plus 6, minus derivative of the denominator times the numerator. So we get d dx s cubed plus 6 multiplied by s squared plus x minus 2, all divided by the denominator square. So the derivative of s squared plus s minus 2 will give us 2s plus 1. Derivative of s cubed plus 6 will give us 3s squared. So now we multiply 3s squared by s squared plus x minus 2. And we also multiply 2x plus 1 by s cubed plus 6. And this is what we get. Then later we combine the terms, and this is what we get. So that will be the final result. Now, this is a concept or table of differentiation formulas, which we went so far. So to find the derivative of a constant value, it's always 0. If we want to find the derivative of a constant value with a function, we'll bring the constant value out, then we find the derivative of f. Now we saw to find the derivative of a product, f times g, it will be the derivative of g times f plus derivative of f times g. Here we said we can do either one first. So I can say derivative of f times g plus derivative of g times f. Either one, it will work because it's plus. Now we saw the power rule. X to the power n always will be n, x exponent n minus 1. Derivative of exponential function is always the same. Then to find the sum, we just find the derivative of each one. So derivative of f plus g will be derivative of f plus derivative of g. Same thing applied to the difference. Derivative of f minus g will be derivative of f minus derivative of g. Quotient, as we just did it right now, f by g, we always have to find the derivative of f first. then we multiply by G, minus derivative of G times F, all divided by G squared. So far, these are all the rules we went through. Again, constant rule, power rule, exponential, constant with a function, sum, product, quotient, and difference. So that will be the conclusion of these lectures. And again, see you in the next lectures.